Welcome students. In this video we are going to find out the atomic packing factor for cubic structure and hexagonal pack structure. So let us start. So how to calculate the atomic packing factor? We can calculate by using this formula. So atomic packing factor is equal to the average number of atoms per unit cell into the volume of the atom divided by the volume of the cube. That is the volume of unit cell, and which is cubical of side A, then definitely it will be A cube. So if I write the average number of atoms per unit cell as N, and volume of the atom we are considered as the spherical one, so it is 4 upon 3 pi r cube, 4 by 3 pi r cube, divided by the volume of unit cell is A cube, isn't it? Now see, to get this value it is very important to have the relation between the atomic radius r and the cube side A, relation between r and A, isn't it? Now let us take the first structure, that is the simple cubic structure. So in simple cubic structure we know what is the value of small n is equal to, it is 1, average number of atoms we have calculated, it is 1. Then here see, the two adjacent atoms are going to touch with each other, okay? So this is the corner atom, okay? And this is the adjacent corner atom. Then they are going to touch. Please remember, they are going to touch. See, we know that this is the side of the cube A and this is the radius of atom R. So we can get the relation between this A and R very easily. That is, you can see here, this R plus R is making the side of the cube, isn't it? That is what we are getting here. This A is equal to 2 times R, or R is equal to A by 2. Very important. Very important. So R is equal to A upon 2. Now put this value here for R, that is A by 2, and calculate the atomic packing factor for this simple cubic structure. You will get N is how much? 1 into 4 pi into R is what? A by 2, that is A cube by 8 into divided by, say, this 3 into A cube. So what we got here? A cube get cancelled, 4 2s are 8, so it is pi upon 6. And C, it is how much? So atomic packing factor pi divided by 6, it is equal to 0.52, isn't it? So atomic packing factor for this simple cubic structure you got as 0.52. And what is packing efficiency? Packing efficiency will be, it is 52.35. So I will write here, multiply by 100 कर दो इसको, so 52.4% will be the packing efficiency for simple cubic structure. Now once you get this packing efficiency, we will get the empty space, isn't it? और voids कितने हैं यहाँ पे? voids होंगे अगर 0.52 ये packing fraction है तो empty space कितनी होगी? 1 minus 0.52, isn't it? So 1 minus 0.52, that is you will get here the empty space in simple cubic around say 47.6%. Please. So in this fashion we can able to calculate the atomic packing factor. So पहले तो हमने निकाल दिया किसके लिए? Simple cubic structure के. Now let us calculate for the body centered cubic structure. So second one is we will find out this packing factor for body centered cubic structure, that is for BCC. So in body centered cubic structure, here the center atom, the center or interior atom is touching the 8 corner atoms. Please remember, corner atoms. So जो इंटीरियर जो यूनिट सेल के अंदर एक कंप्लीट वन जो बॉडी सेंटर पे जो एटम है, इट विल टच द 8 कॉर्नर एटम्स. So we can have here this. So this is unit cell, and so this is the interior atom, body centered atom, isn't it? And it is touching all the corner atoms, isn't it? Like this. So here if I join this diagonal from here to here, isn't it? And this, so see here, this distance A, this is A, this is A, isn't it? Then see here, I will name this cube A, B, C, D, E, F, G, and this is H. So see here how we are going to see this. So see, we are going to find out this distance DG. Okay, so DG, because see here one complete atom is at the body center, the radius R plus R, that is the diameter. Here the radius R, and for this atom this radius R is coming with DF. So DF is nothing but R plus R plus R plus R. It is 4 times R, isn't it? We want to find out this DG. DG we have to determine. But here see, we can have the value of DG in this triangle DCG, in the triangle DCG, in triangle DCG. What you can get using Pythagoras theorem, that is this DG square is equal to DC square plus CG square, isn't it? And DC and CG are what? The sides of the cube, that is A square plus A square. We will get DG square as 2A square. Therefore DG will be how much? Root of this 2A square, root 2 times A. So you got here diagonal as this root 2A. Root 2A, isn't it? And now we can calculate this diagonal DF. This is a body diagonal. Actually DF is a body diagonal of this cube. How to get that? that is in triangle DGF, what we can write by using Pythagoras theorem, that is df square is equal to this dg square plus fg square. So what is dg? dg we calculated here, that is root 2a whole square plus fg is what? A square. So that is 2a square plus a square. You got here the body diagonal df will be how much? df square you get here 3a square, therefore df क्या मिलेगा यहाँ पे? df, that is body diagonal, you will get root 3a. So you get here this value, this r plus r plus r plus r, which nothing but df is equal to how much? So df is how much? 4 times r is equal to root 3 into. So see, for BCC you got this relation between this r and a as r is equal to root 3 by 4 times a. Very important. Many times in the match the pair they will give you the structure, that is simple cubic, body cubic, body centered, then face centered cubic, and they are asking for the relation between this r and a. Very important. Now once you get this relation between r and a, it is very easy to calculate. The atomic packing factor कैसे निकालोगे? Let us calculate. So what is atomic packing factor is equal to average number of atom कितने होते हैं BCC के? BCC average number of atoms per unit cell are 2. That is 2 into 4 upon 3 pi. R is how much? R is root 3 by 4 whole cube into a cube, isn't it? Divided by a cube, that is volume of unit cell. So let us do the simplification. So here a cube is going to get cancelled out. So here 8 pi into root 3 cube, that is 3 root 3 divided by, so 4 cube 64. So 3 get cancelled. So 8 are 64. So here root 3 times pi divided by 8. So calculate this. You will get the value for atomic packing factor for body centered cubic. This is root 3 into pi divided by 8. You got here 0.68. 0.68 atomic packing factor for body centered cubic. कितना आया? It is 0.68. That is here the packing efficiency is how much? Packing efficiency for this BCC body centered cubic structure is 68%. 68%. And what is the empty space? Empty spacing कितना होगा? What is empty spacing in the atoms? We will got it as 100 minus this 68, that is 32%, isn't it? 32%. So this is the atomic packing factor for BCC. कितना होता है? 68%. Very important. Simple cubic के लिए कितना है अपना? 52%, 52.4%. For BCC it is 68%. Very important. Now the next cubic structure we are having, that is the face centered cubic. Face centered cubic structure, that is FCC. And in FCC again the atom on the face is going to touch the atom on the face, because here for every face we are having the one atom and it is going to touch with the corner atoms. It is going to touch with the corner atoms. So this is a face atom which is touching with the corner atoms. So here this radius R, and this side of this unit cell A, isn't it? So we need to find out the relation between this A and R. So see here, this is A, B and C and D. So here this is R, this diameter is 2R and this is R for this atom. And if you use this Pythagoras in triangle BCD, what we can write? So see here, this BD square is equal to DC square plus BC square, isn't it? DC and BC are same, having side A square plus A square, that is 2A square, and BD is how much? R plus 2R plus R, that is 4R whole square, isn't it? So here 16R square is equal to what? 2A square. So R square will be what? 2 by 16 A square. So what will get the relation between R and A? That is R square is equal to A square by 8. So R is equal to A divided by root 8. Therefore R is equal to A divided by this 4 into 2, that is 2 root 2. You get the relation, that is R is equal to A divided by 2 root 2. And what is the atomic packing factor? How to calculate? This is N into 4 upon 3 pi R cube divided by A cube. So what is the average number of atom per unit cell for the FCC? We have calculated, it is 4. So 4 into 4 pi, and R is how much? A upon 2 root 2. So A cube upon this 2 root 2 cube. Okay, so here divided by 3 divided by A cube. So A cube is get cancels. So it will be how much? 16 pi divided by this 2 root 2 cube is how much? So this is 8 into 2 into root 2 into 3. So 16 get cancelled here. So pi divided by 3 root 2. How much it is? So pi divided by 3 root 2. Pi divided by 3 divided by root 2. It is 74%. 0.74. It is atomic packing factor कितना आया? 0.74. So the atomic packing factor for FCC structure is how much? 0.74. That is, what is packing efficiency? So packing efficiency for the FCC is how much? 74%. And what is empty space? Empty space is 26%. So please remember this value. Atomic packing factor for FC structure कितना आता है? 74% is packing efficiency. Atomic packing factor is 0.74. So see, simple cubic 52%, BCC हमने देखा कितना आया? 68%, and FCC we got this 74%. Okay, now after this face centered cubic structure, we are going to see this atomic packing factor for the hexagonal close pack structure. Dear students, now let us see the atomic packing factor for the HCP structure. The atomic packing factor for HCP, hexagonal closed pack structure, right? So let us have this crystal structure. So see here, this is the HCP hexagonal closed pack structure, having 12 atoms at the corner, 2 on the face and 3 at the interior. So see here, I am drawing here these 3 interior. Of course they are in a single plane. ये दिखने में ऐसा दिख रहा है, but they है कैसे? On this plane they are having, right? So the distance from here to here, the basal plane, and from here to here is same. If this total height, that is the distance between the two basal planes here, is c, then this will be the half. From here to here, c by 2, and from here to here it is c by 2. And we know that the distance between each atoms is equal to a. Here a is equal to b, but it is not equal to c, we have seen. Now see here, so from this point or from this atom I am going to join this, and ये जो ऐसा plane है, from this plane I am dropping perpendicular. This atom is like this to this basal plane, so this atom is like this, and from here on this basal plane I am drawing the perpendicular. See, it is like this, right? So this is the basal plane, so here I am drawing the perpendicular. And if I join this atom, this atom, this atom, this atom, and this, so I am getting this tetrahedral structure, isn't it? So it will be like this. See, ये जो atom है, it is like this here. So this perpendicular I can have from here onto this lower triangle or base triangle like this. Okay, and if I join this, we know this distance is how much? C by 2. This distance is how much actually? This perpendicular on the basal plane, it is C by 2, and atom distance between the atoms is A. Say I am having this distance y from this point 2 up to this perpendicular, and this is the right angle triangle, isn't it? So in this right angle triangle, you see this hypotenuse A, this distance y, and this distance C by 2. What we can write? This A square is equal to y square plus c by 2 whole square, isn't it? Now if I take this base or this triangle here, which is equilateral triangle, we are having actually 6 equilateral triangles here, see. So see, 1 2 3 4 5 and 6 equilateral triangles. So I am taking this one where we have drawn the perpendicular, so here, isn't it? So this is our point where we have dropped the perpendicular. So this is the distance y, okay, and if we draw the perpendicular or normal from this point on this side of this equilateral triangle, so it will bisect this side, isn't it? So we know the distance of equilateral triangle, sides are all A, and angle is how much? 60 degree. So this angle will be how much? Is 30 degree, and this distance is how much? A by 2, isn't it? Now we can have the relation between this y or a or y in C, but here we are getting the relation between y and a. What we can write here? This cos of angle 30 is equal to adjacent side is a by 2 divided by hypotenuse y, isn't it? And what is this cos 30? We know it is root 3 by 2 is equal to a upon 2y. So 2 get cancels, so you will get y is equal to a upon root 3. Put the value of y in this equation, what you can get? This a square is equal to a by root 3 whole square plus c by 2 whole square. So we can get a square is equal to a square by 3 plus c by 2 whole square. So we can get here this, take here a square minus a square by 3 into 4 is equal to c square. So 4a square into bracket ax square common निकाल दिया तो क्या रहेगा, this 2 by 3 is equal to c square, isn't it? So you can get the c by a. How much you are getting here? This 8 upon 3 is equal to c by a whole square, and c by a will be root of 8 by 3. If you calculate, you will get c by a is equal to 1.632. So you got here the relation between this a and this height c. Okay, and please remember that here two adjacent corner atoms are going to touch each other. अगर हम देखेंगे, then this is the r and this is the r, and what is the relation between a and r here? A is equal to 2r for this HCP structure. Okay, now we got this relation between c by a. Now we can go for actual finding out the atomic packing factor. Let us see. Now see, what is the formula for atomic packing factor? Atomic packing factor is equal to, we know, the average number of atoms per unit cell multiplied by volume of the atom, that is into volume of atom divided by the volume of the unit cell, isn't it? The volume of the unit cell. So here the unit cell is hexagonal. So if I take this is the basal plane, so here, see here, how many equilateral triangles you are getting here? This 1, 2, 3, 4, 5, 6, isn't it? And for that we can calculate the area of one equilateral triangle. All these angles are 60 degree, of course, isn't it? And if you multiply this area of 6 equilateral triangles by this height c, you can get the volume of the unit cell, isn't it? So just calculate the area of this one equilateral triangle. So the sides are a, isn't it? Just we need to find out the height h, isn't it? So this is the right angle triangle. So we can calculate sine 60 is what? Sine 60. This distance is a by 2, isn't it? So, or we can directly calculate this tan of 60 is equal to how much? This h, height h divided by the adjacent side is a by 2. So what is tan 60? Just calculate. We know what is sine 60. It is root 3 by 2, and cos 60, it is how much? Half, isn't it? So what is this tan 60? कितना आएगा? So it is root 3 by 2 into 2 by 1, you will get it is root 3. So tan of 60 is how much? Root 3. So here you get this h is equal to root 3 into a by 2, isn't it? You get the value of h. Now calculate the area of one equilateral triangle. So area of this triangle, how much? Half into base is what? A into what? The height. How much height? Root 3 by 2 into A. So this is actually the standard formula. The area of the equilateral triangle is equal to root 3 by 4 into side square. So see here, root 3 divided by 4 into this a square. So this is the area of one equilateral triangle you have, isn't it? And to get this volume of this entire unit cell, there are 6 equilateral triangles. So you have to multiply this area by 6 into this height C, then you will get this volume of unit cell. Let us see. So see here, average number of atoms कितने इसमें? There are 6 atoms in HCP. Volume of atom, that is 4 by 3 pi. R is how much? R is equal to A by 2. A by 2 whole cube divided by volume of unit cell. So there are 6 equilateral triangles. So 6 multiplied by 1 area of this triangle, equilateral triangle, root 3 by 4 into a square. Okay, so this is the basal plane area ho gaya ye, into C, isn't it? Now one thing also we know that this C by A is equal to 1.632. So C is equal to what? 1.632 times A. Put the value of C here. What you can get? This 6 get cancels. So we can have this 4 pi into A cube divided by 2 cube 8, that is divided by 3 into 8 into this root 3 into A square divided by 4. I will write this 4 here, into C is how much? 1.632 times A. So this A cube with this A square, A get cancelled out. So we will get how much here? 16 pi divided by 24 into root 3 into 1.632. Calculate this. If we calculate 16 pi divided by 24, 16 pi divided by 24 divided by root 3 divided by 1.632, you will get again 0.7409. So how much you are getting? Again, once again, see, for HCP also your FCC you are getting 0.74, and again for HCP also, see, for this HCP, hexagonal closed pack structure, you are getting the atomic factor is how much? 0.74. So here, of course, then you can have this packing efficiency. How much? Packing efficiency, you got it, 74% for HCP. And empty space is how much? Is again 26%. So this is how we can calculate the atomic packing factor for the hexagonal closed pack structure, which is 0.74. So in this way we have seen the atomic packing factors for the various cubic structures and HCP structure. So let us summarize this. So here will be the crystal structure, and here the atomic packing factor. Match the pair. Tell me for simple cubic, it is 52%. For BCC, body centered cubic, 68%. FCC 74%, and HCP it is 74%. So very important. Okay, thank you.